We're in the middle of hooking up our new program memory module to the program counter we've built earlier. At the moment, we're reading data from the program memory at whatever location the program counter is currently pointing at, but we're not doing anything with the data coming out of that memory yet. Be sure to like and subscribe if you want to see this project unfold. Now let's think about how we can actually make this more interesting. Currently we're just reading out memory addresses and producing the data here, but we're not doing anything with it besides looking at them. If we look up here back at the program counter that we've been building, there are actually all these control signals like the select line, which selects where the program counter basically goes next, if it's like just the next instruction or if it does a jump. We also have these like relative jump addresses. There's absolute jump addresses that we can control. There's some step size down here, some enables. So there's a lot to play with here actually. And what we can do is we can basically connect these control lines, at least some of them, down here to the output of the memory. So let's do that and see what we can do with that. First, let's look at the select line here of the program counter. And let's use bit 0 and 1 of whatever comes out of the memory to drive these signals. So this basically allows us to configure the lower 2 bits of whatever is in memory, and this will control what the program counter does at that point. Another thing we can do is we can hook up the relative jump offset of the program counter to a few bits here in the instruction. Let's say maybe the upper 4 bits. And what this allows us to do is by programming the uppermost 4 bits in memory, we can basically control what the program counter sees as its relative offset. Let's take bit 0 from bit 4 of what's coming out of the memory. Bit 1 is bit 5 in memory. Bit 2 of the jump offset is bit 6 in memory. And bit 3 of the jump offset is going to be bit 7 in memory. What we need to think about is what do we actually do with the upper 4 bits of the relative jump offset, which we don't have any bits at the moment from memory that we can use there. And since it's a relative jump offset and we've been dealing with 2's complement numbers earlier where we want to represent negative numbers, a good thing to do with those instead of tying them to 0, which is basically called 0 extending these 4 bits here, just adding zeros at the top. If we actually sign extended these 4 bits, which basically means that all the upper bits here get connected to the topmost bit of whatever comes out of memory. This has the interesting effect that we are able to represent negative numbers as well. So when we interpret these 4 upper bits here as a signed number, basically meaning that when the topmost bit is set, this represents a negative number. This will actually carry over into the 8-bit relative offset here, and the signed number here will properly be sign extended such that the number that we put on the 8-bit bus corresponds to the same negative number as we've had here. So bit 4 of the relative jump address will be connected to the topmost bit in memory. And the same for bit 5 and bit 6 and bit 7. And what this will allow us to do is basically by programming the upper 4 bits of whatever's in memory, we can control what the program counter sees as the relative jump offset. We can actually interpret these as signed numbers, such that whenever there's a negative number here, we're actually able to produce the same negative number as the relative offset because we've sign extended the value. And then we also want to be able to control what the absolute jump address currently is. Let me bring the lower 4 bits down to our memory module. Basically the same way we connected the relative jump offset over here. Now, in the case of the absolute jump address, we actually want to connect the upper bits that we're not using to 0 because we're not doing any addition on it. So there's no real sense in doing a sign extension here. All right, so that's hooked up. Basically, what we did is bits 0 and 1 of whatever comes out of memory is interpreted as the select lines to the program counter here. And bits 2 and 3 we left unconnected. These don't do anything at the moment. But then bits 4, 5, 6, and 7 of what comes out of memory is fed to the relative jump offset here by sign extending it. So that should allow us to configure a jump offset with the upper 4 bits. But also we're using the upper 4 bits basically as the absolute jump address. So we should also be able to jump to basically a fixed address in memory by just programming it in the upper bits here. So with the setup connected like this, let's actually go back and think about what kind of instructions we can already encode with this kind of very simple scheme of just hooking up individual bytes of the instruction to control signals in the program counter. So this already has to give us some kind of extremely simple kind of redneck instruction set architecture that we can write small programs with that don't do anything useful, but they do something. So let's see what kind of instruction set architecture we can come up with. So the way we have connected individual bits of the instructions to the program counter is as follows. We have 4 bits which are used as various jump offsets, followed by 2 don't care bits, which we can set to zeros or do anything with them, and then 2 mode selection bits. So basically what this means is if we have 2 zeros at the bottom, which is basically the select lines being all zeros, this corresponds to regular stepping mode. If we have a 1 there, that corresponds to a relative jump. And if we have a 1, 0 there, that corresponds to an absolute jump. And 1, 1 we basically don't have connected in the actual hardware. And so this AA, this is basically the relative jump offset, a signed relative jump offset, but also an absolute jump address or jump target. So let's see what kind of instructions we can come up with here. One of the more interesting ones is a no operation, which doesn't do anything really and just steps to the next instruction. Basically, this corresponds to setting the lower 2 bits to 0, so the program counter is in stepping mode, and then just putting any random number up here. But let's pick one. So let's say all zeros is going to be the no op. So let's see if we can come up with a relative jump. So basically what we need to do here is just set the lower 2 bits into relative jump mode. Then bits 2 and 3 we leave at 0 because these are basically don't care and we can do whatever we want with them. And then the upper 4 bits are basically the relative jump offset. And similarly for a absolute jump, we interpret the upper 4 bits as an address. Then the selector bits are going to be 1, 0 to put the program counter into absolute jump mode. So this is jump abs, and it will go to the absolute address A. And we can actually indicate that this is a relative jump by adding a plus here, for example. So this kind of indicates that this is jumping relative to the current program counter address. Now, this is pretty much all we can do with how the instruction bits are connected to the program counter. But there are a few interesting pseudo instructions that we can come up with, which are basically special cases of these nop, jump rel, and jump abs instructions, which have a special kind of semantics. So, for example, one thing that's interesting is what happens if we do a relative jump, but we set I to 0. And what this does basically is it halts the CPU because it tells the program counter to jump to the current instruction continuously, which essentially makes it stop there. So we can use this jump relative here and come up with a halt instruction by saying there's a special pseudo instruction, which is called halt, which corresponds to a relative jump with the upper 4 bits set to 0. And similarly, what we can do is we can look at the absolute jump instruction and think about what happens if the upper bits are all zeros. Well, the program counter is going to jump back to address 0 and continue execution there, which is actually roughly equivalent to doing a reset of the CPU and just starting at the top from the program. So again, we can copy this instruction and fill in the topmost 4 bits as zeros and then call it a reset instruction. And now since we're dealing with hexadecimal numbers, it makes sense to also come up with the hexadecimal equivalent here. Basically, the NOP is easy. This is hex 0. The relative jump is the upper 4 bits correspond to this jump offset, so that's an I. The lower 4 bits are a 1. Same for the absolute jump. The upper 4 bits are the address we're jumping to, and the lower bits are a 2. And then the halt instruction here is basically a 0, 1, and the reset is basically a 0, 2. So this is basically our list of pseudo instructions. And this is the list of actual instructions. So let's see if we can cook up a program with this instruction set that we have here. Now, in an earlier episode, when we were looking at how program counters work and what programs essentially are, we had a small sample program which contained a few add, multiply, and divide instructions, but also some jumps and other things. And we can actually use that program as an example here. And instead of doing adds and multiplies, which we don't have yet, we'll just use NOP instructions. Let's try to come up with something. So at address 0, let's have a NOP instruction, which basically doesn't do anything. Then at address 1, let's do a relative jump, maybe 3 instructions ahead. Let's go there. Again, add a few NOP instructions. Maybe 3 is gonna be enough. And then at instruction address 7, we're going to have another jump. This time, let's do a relative jump backwards. Let's say -5, which is basically going to take us to address 2. And at address 2, let's possibly have another NOP. And then maybe at address 3, let's do an absolute jump. And let's say here we jump to address 8. And then at address 8, let's have another NOP. And then maybe address 9 is going to be our halt instruction. So let's think for a second what this will actually do in practice. So when we reset, the processor will start up here at the NOP instruction and basically execute the NOP, do nothing. Then go to this jump relative. This will jump forward to address 4. 5 and 6 are all NOPs, so they will be executed. Then at address 7, we have a relative jump backwards by 5. So this will transport us back to address 2, which is a NOP again, which is going to be executed. And then we step forward to address 3, which is an absolute jump to address 8, which is going to take us down here to this NOP. And the next program should basically just halt at address 9. All right, so what we have to do now is basically assemble this program into the actual bits and bytes that we have to program into the flash memory that we have. So let's start from the top. A NOP is just zeros. A relative jump has the lower 4 bits set to a 1, and the upper bits are basically the jump offset. In this case, it's a 3 because we want to jump 3 ahead. Then NOP, we already know, is 0, 0. The absolute jump has a 2 down here in the lower 4 bits, and the upper 4 bits correspond to where we want to jump to, which is an 8 in this case. Then again, a lot of NOPs, which we know how to deal with. And then this one here is interesting, the relative jump, but this one is backwards. So we already know that the lower 4 bits are a 1, but the upper 4 bits, we need to come up with what the 2's complement of 5 is. So basically, what is -5 in binary in 2's complement arithmetic? So 2's complement is pretty interesting. So let me bring up Python again, because it's quite handy to toy with these things. So a 5 in binary is 0101. And taking the 2's complement, which is basically finding the negative of the number, is essentially just flipping all the bits in the number and then at the end adding a 1 to the result. And we can ask Python to do this for us. So we can ask it to give us a binary representation of -5. And if we do this like this, we will get a minus and then the binary for 5. But that's not what we want. We want the 2's complement. So what we can do is we can force Python to actually cram this into a 4-bit number, which is going to give us what we're looking for. So what's the hex version of that? It's a B. So we go over here back to our program and we type a B for the relative jump offset. The knob, we already know how it works. It's all zeros. And then the halt pseudo instruction was a 0, 1. Let me also write down the binary representation of the instructions. So it's a bit easier to know what we're looking at when we see this coming out of the memory and displayed on the bar graph LEDs. And now another thing we might want to do is these knobs, they all look the same, right? It's like 0, 0, 0 everywhere. And that's a bit dull because we can't really tell which part of the program we're looking at. But what we can do is we can, well, basically we said that the knob instruction, we picked the upper 4 bits to be a 0, but basically they can be anything. So let's, for example, say the first knob has a 1 in the upper 4 bits. The second knob will have a 2. The third knob will have a 3. The fourth knob will have a 4. The fifth knob will have a 5. So we can basically follow along and understand what kind of knob we're looking at. And then this knob will have a 6. So this is our first little program here. So let's write the assembled version of this program into the ROM file we had open earlier. First up is the knob, that's a 10. 31 is the relative jump. Another knob, jump absolute. Another knob, another knob, another knob. Our relative jump backwards. And then we go to address 8 over here. And this is another knob. And a halt instruction. All right, so let's get this first simple program of ours programmed into our flash memory. Let's first convert the hexadecimal version back to binary. And then use MiniPro again to actually write this to the flash chip. Let's see if this works. So let's power this back up and step through the very first program. We start out at address 0, and correspondingly address 0 is our first knob instruction, hex 10, which is 0001, and then all zeros. So what this does is it configures the select line to just be in the normal stepping mode, which is going to cause the program counter to just step to the next instruction. And the upper bits are just ignored, and this one here, this is just for us to identify that this is the first knob in the program, just so we have a visual reference. So let's step everything out of reset. 1, 2, 3, 4. And now when we hit the step button, this program counter should increment to 1, which is basically executing the knob. And then we should see the next instruction down here. All right, so this is a 1. And indeed, down here, we see the next instruction. This is the jump relative that we've programmed, with the 2 1s at the top indicating that we want to jump 3 instructions forward. And the 1 down here basically just indicating that it's a relative jump. So when I hit the step button, what we expect to happen is that the program counter should jump forward to address 4, basically the one it's currently at, plus this 3 that is encoded in the instruction. Address 4 is a NOP again. This time it's NOP number 3. And there are 3 NOPs in series, so we should be able to step through those. So this is the first NOP there, the second, and the third NOP. As you can see, we stepped through the instructions just linearly by incrementing by a single byte. But now we are at address 6, so this is the last NOP. If we step one further, we are at address 7. And address 7 in our program is another relative jump, which is indicated by this 0001 at the bottom here. But this time it's a backwards jump. So basically the number we have up here is -5, and we're trying to jump back to address 2. And there you go. As soon as I hit the step button, the program counter goes back to address 2. Address 2 is a NOP again. So if we step over this NOP, basically execute the NOP, the program counter advances to address 3. And address 3 is an absolute jump, which is indicated by this 0010 at the bottom here. And where are we jumping to? Well, basically the upper 4 bits of the instruction. So this is a 8. So if I hit the step button, we should basically be just copying these upper 4 bits into the program counter. So address 8 is another NOP, as you can see here. And if we step over that NOP, we basically arrive at the last instruction, which is at address 9. And this instruction is a halt, which is a pseudo instruction. And all a halt is basically a relative jump with an offset of 0. So it's continuously jumping to the current address. So basically making the processor stuck in a loop. Let's see if that actually works. So we have the 0 up here, which is basically the jump offset. And the 01 down here indicates a relative jump mode. So if I hit the step button, the program counter should not move. And nothing happens to the program counter. And I can basically put this into run mode. And since we are at a halt instruction, nothing happens and the program is basically finished. But what we can do is we can hit the reset button here. And basically the program should start from the top and just re-execute the steps that we've seen just now. Now, one thing we can do, which might be a bit more interesting, is instead of having a halt instruction at the very end of the program, which basically makes the CPU stop doing anything, we can put a reset instruction in here, which will cause it to basically start at the top with the program and just re-execute it. This will cause it to basically run in a loop because the program will run through, it will reset and run through again and then never stop. So let's try that. So let's go in and modify our program. Instead of a halt, let's have a reset down here. And let's also go to our ROM and make sure that this reflects the change. So instead of the halt, we have a reset. And let's program this onto the chip again. Perfect. Let's power this back up. Step it out of reset. And now let's see what happens when we reach the final location of the program. So this is our NOP, jump relative +3, which takes us to address 4. Then we have 3 NOPs in a row. Then address 7 is a jump relative, but this time backwards to address number 2. At address 2 we have a NOP, followed by an absolute jump, this time to address 8, which still works. And then step over the NOP. And now address number 9 is a reset instruction, which you can see down here. It's a 10 at the end instead of a 01, which indicates that it's the reset pseudo instruction. So if I hit the step button now, the program counter should basically go back to 0 and start again with the program. And there you go. So we can let this run, and it will just loop. Awesome. Our CPU recognizes a few rudimentary instructions and knows how to execute them. And we have a handy flash memory that we can load the program into. However, we're limited to 4 bits of jump addresses and offsets, and we're already using 6 out of the 8 total number of bits in the instruction just to be able to jump around the program. We're not even doing any real work yet. So in the next episode, I would like to take a closer look at a more clever way to encode instructions and probably make a case for why we want our instructions to be 16 bits instead of just 8. Thanks a lot for watching, like and subscribe if you'd like to see more of this, and see you next time.